So let's talk about vaporization and vapor pressure. So vaporization is when something goes from a liquid into the gas state. That could happen at room temperature because we know that water will evaporate even though it's not boiling. It can also happen when a liquid is boiling. So here we have an illustration of a beaker of water. And of course this is a static picture so we can't see the movement. But these water molecules here are vibrating, they're jiggling, and they're also moving around relative to each other. They have kinetic energy. Some of them are moving, up, some are moving down. They're moving in all directions. If we have a molecule that's at the surface of the liquid and it's moving up and it has enough energy, it can escape from the liquid and go into the gas state. Did you guys ever play the game Red Rover in school? You made it through before they banned games like that? So if you're not familiar with Red Rover, two groups of children out on the playground, they form two lines and they hold hands, parallel lines, and then somebody in one line says, Red Rover, send Sally right over. So Sally runs across the open space and tries to break through the line. You can imagine how wrists could get broken, right? Or at the very least, there could be tears. So Sally's running at the other line. So this surface of the liquid I think of as being a Red Rover line. In order for these molecules to escape, to get through the Red Rover line, they have to be going in the correct direction. If Sally runs away from the line, she's not going to break through, right? If these molecules are moving away from the surface, they can't escape. If they're moving towards the surface and they have enough energy, they can break loose. Does that make sense? So these molecules up here broke through the Red Rover line. The Red Rover line is held together in real life by children holding hands. But what holds these together are the intermolecular forces between the molecules. Different compounds have different strengths of intermolecular forces. Just like if you had Red Rover lines from children in different grades, it would be harder or easier to break through. If you've got a line of kindergartners, you're not going to have to run as fast as if you've got the sixth graders, right? So I'm probably getting ahead of myself, but I really like this picture. So those are escaping. Now, in the gas state, these molecules, kinetic molecular theory tells us, they're going to move in a straight line until they run into something. With this beaker being open, most of them are probably going to leave. They're just going to go off into space and be gone. But some of them may come back and collide with the surface of the water, and then they get trapped again. So vaporization is leaving, going from the salt liquid to the gas state. Condensation is when a gas molecule gets trapped into the liquid again. And I forget who said this, but someone described at the molecular level, it's a wild dance floor there at the molecular level. So you could think of this as a crowded dance floor, and people are moving. It's an upbeat tune, and people are enjoying themselves. And so that's what's happening here. There's wiggling and jiggling, and there's also movement across the floor. Okay. So if we think about the average energy, the kinetic energy of those particles, some of them have higher energy, some of them have lower energy. Just like, if you looked at those people dancing, some of them are like really vigorous or hyper, and other people are just kind of doing some chill dancing, right? So we have some higher and some lower, but we could look at the average kinetic energy. So here what we're showing is a distribution. So this blue curve here is the distribution of thermal energy at a lower temperature. So the average would be around in here somewhere. If we increase the temperature, we increase the kinetic energy, we increase the movement of those molecules. So that's like, I don't know, giving everybody on the dance floor an energy shot or something, and all of a sudden, they're like stepping it up a notch, right? So we've increased the amount of energy. Temperature is a measure of that average kinetic energy. The other thing that happens when you increase the temperature is the distribution broadens out. So you still have some with very low energy and some with much higher energy, but the difference between those gets bigger. This curve broadens out as you increase the temperature. We've drawn a line here. This is the minimum kinetic energy needed for those molecules to escape under these conditions. So at a low temperature, under the area under the blue curve here is the number of molecules that, if they get to the surface, have enough energy to escape. It's just a small number of them. Most of them, doesn't matter where they are in that liquid, they're just stuck. They can't run fast enough to break through the line. So they may run at the line, but they just get bumped back. When we increase the temperature, the average kinetic energy goes up, but even more so, it broadens out, and so we have a large increase in how many molecules have enough energy to break free. So at a higher temperature, we're going to have a lot more molecules that can break loose. So vaporization will occur more quickly at a higher temperature. So, public restrooms, a lot of them don't have paper towels anymore. They have these hand dryers. And the sort of standard hand dryer blows warm air on your hands. Why does it do that? Because water vaporizes more quickly at high temperatures. When you have wet laundry, you put it in the dryer, and the dryer heats the clothes because they dry faster that way. Clothes will dry at room temperature, but it can take a long time, right? And so by heating them up, you cause evaporation to occur more quickly. Any questions? Another way to increase the rate of vaporization is to increase the surface area. The particles have to have enough energy to break loose, but they also have to be able to get to the surface. And so if you have more surface area, that means you have more molecules at the surface. You're going to have more molecules that are able to escape. The other thing about the surface is those molecules are held less tightly because they are only held on the sides and below. There's nothing holding them above. And so there's less attraction than for the ones that are in the middle. That explanation doesn't really help me out much at all, because how could it evaporate if it's not at the surface? Well, it can, but it doesn't. So liquids that have stronger intermolecular forces evaporate more slowly, because at the same temperature, if you have really strong intermolecular forces, that's like the 6th grade line of Red Rover, you have to run a lot faster, right? So if we're looking at this graph here, if we have stronger intermolecular forces, that's moving this line over to higher energy. And so then you're going to have fewer molecules with enough energy to escape. So the rate of vaporization is going to go down. If you have weaker intermolecular forces, that's equivalent to moving this line over here. So we move the line over here, and now a lot of the molecules, maybe even most of them, have enough energy to escape. The vaporization is going to occur very quickly. So we have 2 words that qualitatively describe this: volatile and non-volatile. So volatile means liquids that vaporize easily, non-volatile liquids that do not vaporize easily. So example of a volatile liquid would be like rubbing alcohol. You go to the doctor and they're going to give you a shot, and they take this little wet pad and they wipe it on your skin, right? Because to clean it and get rid of any germs. And it feels cold, and it doesn't stay wet. You look at it, it's like, oh, it's dry already. Because alcohol has weaker intermolecular forces than water, and so it vaporizes, it evaporates very quickly. It's a volatile liquid. Gasoline is a volatile liquid. If you accidentally spill some gasoline, say while you're pumping gas, and if you were to try to go get some paper towels or something to wipe it up, by the time you came back, it's gone, right? Because it just vaporized. It has a very low, very weak intermolecular forces. Non-volatile liquids do not vaporize easily. Let's think about maybe vegetable oil. So if you have a rag soaked with vegetable oil and a rag soaked with water, and you leave them on the counter and you come back 2 days later, the one that was wet with water is going to be dry, right? All that water will have evaporated. What about the one with oil on it? It's still just sitting there with oil on it, right? Maybe attracting ants or something. Oil doesn't evaporate because the intermolecular forces that hold it together are stronger. Okay? Any questions? So energy is associated with vaporization and condensation. So now we've got that beaker of water in our heads. Let's insulate the beaker so that no energy from the surroundings can come into it or escape from it. And let's think about the molecules of liquid water evaporating. Which molecules are evaporating? The ones with the high energy or the low energy? The ones with the higher energy, right? They've got enough energy to get through. So we're losing the high energy molecules. What does that do to the average kinetic energy of the rest that are left behind? It goes down, right? If you had a bunch of kids playing Red Rover and all the fast ones have already gone and broken through the line, and now you're left with all the slow, pokey kids, right? The average speed of these children now is lower because all the fast ones left. So if we're losing the high energy molecules and the average kinetic energy is less, what does that tell us about the temperature of the liquid? Temperature is a measure of average kinetic energy. So if the average kinetic energy is less, the temperature is less. So if you have water evaporating where it cannot absorb energy from the surroundings, the temperature of the water will go down because it's losing energy. So vaporization is an endothermic process. It requires energy to go in, because if it's not insulated and the temperature drops, what happens? Energy will flow from the surroundings and bring the temperature back up. So energy goes in. Endothermic process. This is why sweating cools your body. So you get sweaty. It's been really warm lately. And so we get sweaty and you get a little breeze. And what do you feel? You feel a coolness, right? Because when the sweat evaporates, it's taking away the higher energy particles, lowering the temperature. And then your body says, oh, here's a low temperature place, I'll send some of my heat over there. And so it cools you off. So vaporization is endothermic. Condensation is the opposite of vaporization, so it must be exothermic. And this is not something that is necessarily obvious to us. But when a gas condenses into a liquid, it releases a great deal of heat. So if you have, maybe you're making pasta for supper and you've got a pot of boiling water, is it going to be pleasant if you stick your hand in the steam above the boiling water? Is that going to feel good? Not for very long, right? If you're super cold, it might feel good initially, but it's going to get very hot very quickly. Because as that hot steam, high kinetic energy steam, hits your hand and cools down, it releases the energy that it had into your skin and can cause pretty severe burns. So condensation is exothermic, releases energy. Vaporization is endothermic, absorbs energy. This cycle with water moderates our climate. It moderates the temperature. So I pulled this up. This isn't in your book. So we live in Fresno, and here's the, I pulled this from the internet. Average temperatures in July from 1971 to 2000. Average high 96.6 Fahrenheit, low 66.1 Fahrenheit. The difference there, 30 degrees. Living here, you'd probably say, yeah, that's typical. Big temperature swings, right? So my husband and I lived in the San Francisco Bay Area for 3 years. And this is typical of what you'd see in San Francisco. In July, average high temperature, 68 degrees. It's cold, right? The average low, 54. Temperature difference, 13.8 degrees. The temperature does not change as much over the course of the day. Why is that? It has to do with the energetics of vaporization and condensation of water. So here in the Central Valley, we do not have large bodies of water around, and our relative humidity is generally pretty low. I think yesterday it was like 22%. Other parts of the country, humidity can get up to 90, 95, 100%. And there you sweat and it doesn't do any good. But here you sweat and it cools you off pretty well. So what happens here, the sun comes up and shines down on the Central Valley, and things absorb energy from the sun, and things get hot very quickly, right? And then as soon as the sun goes down and stops putting that energy in, things are releasing their energy and the temperature drops very quickly. If you have high humidity or an area like San Francisco, which is surrounded on 3 sides by a huge body of water, you have the water condensing and evaporating that moderates that temperature. So as the sun beats down on San Francisco, it also beats down on the bay around it, and the bay, the water, absorbs the energy. Some of it evaporates, but it absorbs the energy, and so it doesn't get as warm. Then at night when the sun goes down, the air temperature gets cooler, and now we've got water condensing back into the bay and onto surfaces, and that releases energy and keeps the temperature from dropping as low. So places where you have higher humidity or are surrounded by large bodies of water, or even just near them, they're not going to have these huge temperature swings that we do here. If you've grown up here, you probably think that this is normal, and it's normal for here. It's not normal for the rest of the country. Some places, yes, but a lot of places, 30, 40 degree temperature change during the day, that's big news. A lot of places, it's more like 10 degrees. Any questions? So, of course, if we have energy, we can quantitate that. So the heat of vaporization, or the enthalpy of vaporization, it's delta H again. This is delta H associated with turning something from a liquid into a gas. So if we look at liquid water going to water in the gas state, that's an endothermic process. It requires an input of energy. We call that delta H vap, heat of vaporization. And for water, it's 40.7 kilojoules per mole. It's pretty high. So down here in this table, we see several different liquids. There's water, rubbing alcohol, acetone, diethyl ether. And here we have the delta H at the boiling point and delta H at room temperature. This is always a positive number because vaporization always is endothermic. It is somewhat temperature dependent, but not as much as you might think. So at the boiling point, water has a heat of vaporization of 40.7. At room temperature, it's 44, a little bit higher, but not much. So we vaporize the water. It absorbs 40.7 kilojoules per mole. If we take that same water and we condense it, conservation of energy says we can't create or destroy energy by just heating water, vaporizing and condensing water. When we condense a mole of water, that same amount of energy has to come back out. So condensation, we just change the sign. We don't have a special name for that because it's just the opposite of vaporization. So we can use the heat of vaporization as a conversion factor to look at moles of substance and the amount of heat involved in vaporizing or condensing them. So calculate the amount of heat in kilojoules required to vaporize 2.58 kilograms of water at its boiling point. Well, we need to look up the heat of vaporization. So the heat of vaporization for water is, I'm not going to put the plus in there. It is plus, but 40.7 kilojoules per mole. You look it up in the table, or it's given to you in the problem. If it helps you think about it, you could write out the equation. You've got H2O in the liquid state going to H2O in the gas state. And this heat of vaporization says that for 1 mole of water, liquid going to steam, it's going to take 40.7 kilojoules. So what we've got here in this problem is we're given a mass of water. So we've got 2.58 kilograms of water. This is dimensional analysis. That's the only number given in the problem. What are they asking us to calculate? Kilojoules, right? So to solve this problem, we don't look up an equation. We just look at, well, how can I convert these units? And sometimes you need to start at the beginning, and sometimes you need to start at the end and work backwards, and sometimes you work both and hope you meet in the middle, right? So heat of vaporization, because that's in the title, we're probably going to need that. Heat of vaporization has units of kilojoules per mole. I want kilojoules here, so the unit I want before that is going to be what? Moles, right? Because if I had the moles of water, I could use this to find the kilojoules. So I need moles of water, I've got kilograms of water. Well, what are we getting good at converting moles to? Grams. So if I had grams of water, I could convert to moles using a molar mass. Can I convert kilograms to grams? Sure, heck yeah. So there's my path. Any questions? Once you've got that written out, you just follow the pattern. I've got 3 arrows. I'm going to have 3 conversion factors. So I write down my starting number, 2.58 kilograms of water, and I'm going to have 3 factors here. These are the units that go on those. I'm going kilograms to grams to moles to kilojoules. Kilograms to grams to moles to kilojoules. And then what I want is for this unit to go away. I need it to cancel out, so I'm going to divide by this unit over here. So I divide by that unit, because then kilograms will cancel. And I need grams to cancel, so I put, bless you, grams down here. And I need moles to cancel, so I put moles down here. I think that's really cool. So there we got all the units working out. At this point, you go to put the numbers in, because the units are going to tell you where to put the numbers. You don't have to think about, well, am I supposed to multiply by the heat of vaporization or divide by it? You just stick it in where the units tell you. So here the heat of vaporization, 40.7 is with kilojoules. So over here, I'm going to write 40.7 with kilojoules. No thinking involved. Here, kilograms to grams, what we need to remember there is, what does kilo stand for? Times 10 to the what? 3. So K is an abbreviation for times 10 to the third. So this has got kilograms on the bottom, it's got grams on the top. The idea of dimensional analysis is that the thing on the top has to equal the thing on the bottom. So a gram is not the same as a kilogram. But I can put the meaning of kilo on the top, times 10 to the third. I've got 1 times 10 to the third grams is equal to 1 kilogram. Kilo is a nickname for times 10 to the third. There are other ways to do that conversion, but I see a lot of students mess them up. So if you always put the prefix on one side and put the times 10 to the something that it stands for on the other side, it'll be correct every time. Then in the middle, grams and moles, that relationship is the molar mass. So you calculate that for water. 2 times the mass of hydrogen plus the mass of oxygen, it's grams per mole, and so 18.02 grams of water is equal to 1 mole of water. If it bothers you that there aren't any numbers up there or down here, just stick a 1 in there. Any questions? So if you haven't gotten the hang of dimensional analysis yet, it's not too late, okay? It's kind of why I sort of went through this in a more detailed way than is really warranted at this point in the semester, because I know that for some of you this is still kind of a fuzzy topic, and it is just so important and valuable that I want you to figure it out. So if you're still like mystified by this, please talk to me. I mean, I can only do so much talking to the whole group. I can do a lot more one-on-one with you, answering questions. So to solve this on my calculator, I'm just going to start at the left and move across, and as I come to a fraction, I multiply by the top and divide by the bottom. And of course, you can skip the ones if you want. So 2.58 times 1 EE3. And if you're not using scientific notation on your calculator correctly, that's going to cause some issues. Not every time, but sometimes. And then I'm going to divide by 18.02. And I'm going to multiply by 40.7. Press equals. And my calculator gives me a big old mess, a whole bunch of digits. This is where significant figures come in. So I look at this, and this has 3 digits. It's 3 significant figures. This is an exact conversion because it's just metric units. This is not exact, but I've got 4 digits there. And this one also is not exact. I've got 3 digits. So I'm multiplying and dividing. It's the smallest number of digits of significant figures, so 3. So that means in my answer I should have 3 significant figures. So what I'm going to do is I'm going to keep that in my head as I write this down. So writing it down, I've got 5, 8, 2. That's the third one. And then I'm going to keep going. I'm going to write down at least 2 more digits. You can write all of them down if you want, but that gets really tedious. If you write down 2, you don't even have to worry about rounding the last one. You just write it down. The next one's a 9. I'm not going to round that one up to a 2, and it's going to be fine. And then my unit is kilojoules. It's kind of an ugly J. Then to round this to proper scientific notation, I want to keep this 2. The 2 is in the tens place. So what I'm doing is I'm rounding this number to the nearest 10. So these are just regular numbers. Yes, it's an amount of kilojoules, but this is just the regular kinds of numbers that you used in elementary school. So this is 5,827.1. If I want to round this to the nearest 10, it's closer to 5,830 than it is to 5,820, right? Because the next digit is a 7. So I could call this 5,830 kilojoules. What I see people do that just is so frustrating to me is they'll tell me that this is 583. It's not 500. It's 5,000. You wouldn't round things like that with money because you would recognize, hey, wait a minute, this isn't working. And yet students do stuff like that with like kilojoules and grams and things because I don't know why. So if that happens to you a lot, then what you should do is put this number in scientific notation. It's a problem anytime you're rounding to the tens, hundreds, thousands, anything bigger than the ones place. If it's ones, tenths, hundredths, people don't seem to have an issue with it. So you put this in scientific notation. So I'm moving the decimal point 1, 2, 3. So 5.8. I'm going to round that 2 up to a 3. There are my 3 digits times 10 to the, and I count how many places I moved it. 1, 2, 3. So either of those answers is really nice. Any questions? So we talked about water evaporating in an open beaker. What about in a closed container? So here we have an Erlenmeyer flask with a stopper in it. So we've got our water here. It's got its average kinetic energy. Some of the molecules have enough energy to escape, and if they get to the surface, they can escape into the gas state. They break through that red rubber line, and they're loose. These gas molecules now, though, will travel in a straight line until they bump into something. This container has a finite volume. It's got a stopper in it. They can't escape into the atmosphere. They're going to hit something, and maybe they'll bounce around up here a little bit. Eventually, they're going to hit the surface again. Like little astronauts, splashing down into the ocean. They're going to get trapped, okay? So when these gas molecules collide with the surface, that's condensation. So you have evaporation and you have condensation happening at the same time. Initially, you only have evaporation because there aren't any water molecules up here to condense. Evaporation is only dependent on temperature, and so the rate of evaporation is just going to stay the same. The rate of condensation is going to depend on the concentration of gas molecules, or how many gas molecules there are. If there are a whole bunch of them up here, then a whole bunch of them are going to be colliding with the surface at any time. If you only have a few will be colliding with the surface. Does that make sense? So the more crowded this gets, the faster the rate of condensation. So we've got evaporation occurring at a steady pace, and as more and more gas molecules come up here, the rate of condensation increases and increases. At some point, the rate of evaporation and the rate of condensation will be equal to each other. You have particles getting into the gas state as fast as they're going back into the liquid state. And when that happens, you're going to have a certain pressure of gas because gases exert pressures. So if I have water vapor here, it's going to exert a pressure. The pressure is related to its concentration. And this vapor pressure here will become constant. What I've got is a dynamic equilibrium. You've got molecules condensing and evaporating, and so there's a constant turnover of molecules, but at any given point, the number of molecules in the gas state is going to be the same. So this reminds me somehow of a busy airport. And you've got people taking off, and you've got people landing, right? And you've got flights coming in and flights going out. And if you took a snapshot of the airport and counted all the people at any given point, it would probably be roughly the same number of people. because you have people coming in and people going out. It's not the same people all the time. Yeah, there's some people working there that were there all day, but most of the people are coming and going, right? And so it's this turnover, and it's about the same number of people because they're coming in as fast as they're leaving. Does that make sense? So we can look at that in a graph form. So here the red line is the rate of evaporation. So as time goes on, the rate of evaporation stays the same. The rate of evaporation only depends on the temperature of the water, the average kinetic energy of the particles. If the temperature is not changing, then the rate of evaporation won't change. In that flask, the surface area can't change, so that's not an issue. The rate of condensation initially is 0 because there are no gas molecules to condense. As time goes on and evaporation proceeds, the rate of condensation will increase. You're getting more and more gas molecules, but at some point in time, the rate that you're making gas molecules is going to equal the rate at which you're condensing them back into the liquid. And at that point, you have a dynamic equilibrium. Equilibrium, it's balanced. Dynamic, it's not a static thing. It's not that everything's frozen. There's stuff going on, but it's balancing out. And so vapor pressure is the partial pressure of the gas that's in dynamic equilibrium with its liquid. The vapor pressure will depend on the strength of the intermolecular forces. If you have a volatile liquid with very weak intermolecular forces, it's going to have a high vapor pressure. You'll have a lot of it in the gas state. If you have something with strong intermolecular forces, it's very hard for the molecules to escape from the liquid. You're going to have a low vapor pressure. That vapor pressure is going to remain constant. It doesn't matter what the size of the container is or the shape or anything like that. So we can look at this in terms of Le Chatelier's principle. If we have a container here where we've got, I think this is pentane maybe, liquid pentane and gas pentane, and we've got an equilibrium established. There's a pressure of this gas that's related to the number of molecules that are in the gas state. If we increase the volume of the container, the volume of the liquid's going to stay the same. But now the volume of the gas has gotten a lot larger, which causes the pressure to drop. When the pressure drops, then the rate of condensation goes down, because now we have those molecules in a much larger area. As they're bopping around, you can imagine that they're not going to run into the surface of the liquid and condense as quickly because they've got more space to run around. So what will happen? Well, the rate of evaporation continues on the same. So the rate of evaporation will replace or add molecules in the gas state until you get to that same concentration again, that same vapor pressure. If we push down on the piston and cause this to have a smaller volume, that's going to increase the pressure of the gas. That will increase the rate of condensation. Rate of evaporation isn't changed. Rate of condensation increases, and so all that extra squished together gas, some of it will go into the liquid state, and it'll get back to this vapor pressure that it always wants to have. Make sense? Any questions? We talked about Le Chatelier's principle before. Yeah? Okay. So there's a relationship between vapor pressure and temperature. When you increase the temperature of a liquid, you increase the rate of evaporation or vaporization. The rate of condensation does not change with the temperature significantly, but the rate of evaporation increases. So if we're looking at this graph, if we increase the temperature, what we're doing essentially is we're putting the rate of evaporation up here. And the rate of condensation will keep going on this curve until it runs into the rate of evaporation. But you're going to have more in the gas state, and so you're going to have a higher vapor pressure. So this graph is showing us vapor pressure and torr of several different liquids as a function of temperature. So for water at room temperature around 20, 25 degrees, the vapor pressure of water is very low. It's, I don't know, like 20 torr or something. It's very small. As you increase the temperature of the water, as you heat it up, the vapor pressure goes up. When you get to 100 degrees, the vapor pressure of water is equal to normal atmospheric pressure. We'll talk about that in just a minute. Different liquids have different curves, they have different relationships. Ethylene glycol has very low vapor pressure, it's not very volatile. Diethyl ether is very volatile. It boils at 34.6 degrees Celsius, so just above room temperature. And so you can look at these curves. Ethyl alcohol is more volatile than water. But a small change in temperature can give us a big change in vapor pressure. The boiling point of a liquid is the temperature at which the liquid's vapor pressure equals the external pressure. So if it's open to the atmosphere, 1 atmosphere or 760 torr of pressure. At that point, the molecules that are on the inside, in the interior, not just the ones on the surface, but the ones in the interior, have enough energy to break loose. And they're going to form little pockets or bubbles of gas within the liquid. And those, of course, are much less dense, and so they'll rise to the surface, and the gas will escape. But that's what's happening when water is boiling. We've reached a temperature where the vapor pressure of the water is the same as the vapor pressure above, 1 atmosphere. And so the vaporization will occur everywhere within the water, and we'll get these bubbles. The reason you see them forming mostly on the bottom in a situation like this with a coffee pot is because the source of the heat is at the bottom, and so that's where it's the hottest. That's where it's 100, and up here it's actually a little cooler. That's why we're not seeing bubbles forming everywhere. So as you increase the temperature of the water, the vapor pressure increases. For water, the vapor pressure is 760 at 100 degrees. For ethyl alcohol, the vapor pressure hits 1 atmosphere or 760 torr at 78.3 degrees. And so that's where it begins to boil. Diethyl ether hits 760 torr of vapor pressure at 34.6 degrees Celsius. Weaker intermolecular forces. So what we define as the normal boiling point of a liquid is the temperature at which its vapor pressure is equal to 1 atmosphere. So that's 100 degrees for water. So here on the valley floor, atmospheric pressure is about 1 atmosphere. We've got a barometer here. It's 29.58 inches of mercury. 29.92 is exactly 1 atmosphere, so very close. What happens to the barometric pressure as you go up into the mountains? It gets lower. The atmospheric pressure gets lower. So what if you went up really high in the mountains until you had 600 torr of pressure? External pressure now is 600 torr. Is that going to affect the boiling point of the water? Yeah. The water's going to boil here. We can change the boiling point of water by changing the external pressure. So if we're at a high, I didn't mean to do that. If we're at a higher elevation, the water's going to boil at a lower temperature. So here it looks like it might boil at around 90 degrees Celsius. Is that going to affect the cooking time of foods? Yes, it will. That's why if you look, especially for baking, if you look on the package, it'll usually have a little thing at the bottom, high altitude instructions, because you need to do things a little different at high altitude. We're talking about things like places like, Denver, a mile up. So this is called a heating curve. We're looking at the temperature of the water as we're adding heat. So we're starting at room temperature, 20 degrees Celsius, and we're adding heat. So as we add heat, the temperature goes up. And if you remember the relationship there, Q equals MC delta T. So we have a specific heat capacity for water, and the mass and the change in temperature is going to depend on how much energy is put into it. It's a linear relationship. When we get up to 100 degrees, as we're heating this up, the vapor pressure of the water is going up. When we get to 100 degrees, the vapor pressure is now equal to the atmospheric pressure, and the water begins to boil. It's the high energy particles that are leaving as the water boils. If we were not putting any energy into the water would cool down and stop boiling. But we're still adding heat. All the heat that we're adding is going away in those high energy particles, and the temperature is going to stay at 100 degrees. This is something that's not immediately obvious to most people. If you take a pot of boiling water and it's been boiling for 1 minute, or you've got a pot of boiling water that's been boiling for 10 minutes, they are the same temperature. Doesn't matter how high you turn up the burner. You can make it boil more vigorously, but they're both 100 degrees Celsius. The temperature will not go above 100 until it's all been converted to a gas. If you continue to heat the gas, then the temperature will go up. So this has a lot of implications for cooking. We got an Instant Pot about a little over a year ago. My husband does most of the cooking, thank goodness. He's awesome. We got an Instant Pot. An Instant Pot is essentially a modern electric pressure cooker. It's got a lid that seals on, and so when you boil water, it is closed into the container. So let's go back to this graph. So as the water boils and the vapor pressure builds up, the pressure's going to go up, and now we've got a higher pressure than atmospheric pressure, and that causes the boiling temperature of the water to increase. So in a pressure cooker or an Instant Pot, you can get water to boil at a higher temperature. If you cook something at a higher temperature, it cooks faster, right? When you've got things with a lot of liquid in them, or things that you cook in liquid, if it's open to the atmosphere, you can't get it above 100 degrees Celsius. And so that very much limits how fast you can cook things. Why is it faster when you deep fry something? How hot is the oil? Oil is really hot. It's a lot hotter than water. I mean, you just put your hand near it, they're both really hot, right? You don't want to touch them, it's going to damage your skin. But if you use a thermometer, you can get that oil much hotter. What happens with oils is it's not going to boil, it'll start to smoke and eventually burn. but you can get oil much hotter than water. You can get it like 300 degrees Celsius. So that's going to cook your food a lot faster. So an Instant Pot, by having a sealed lid and allowing the pressure from the water vapor to build up, can cause the water temperature to go up as it's boiling. So, yeah, I already said that. The relationship of vapor pressure and temperature is not linear. We can see that, right? Those aren't straight lines. That's vapor pressure versus temperature, not a straight line. Well, chemists, scientists in general, we like to come up with equations to describe things like that. It's an exponential curve where the vapor pressure is equal to a constant E times E raised to this power where temperature is up here. It's a complicated relationship. We can take this equation and rearrange it. What we're doing here is we're putting it into the form of a line. Y equals mx plus b. So here what we have is the natural log of the vapor pressure is the y value. 1 over t is the x value. If you graph these, you get a straight line. The slope of the line is equal to negative delta H over R. R is the gas constant. The intercept is the natural log of beta. That's a constant. We don't really care about that. But the slope, we can get the heat of vaporization for this thing by measuring the vapor pressure at different temperatures and graphing it. Very cool. Here's an example of a graph. So here we have natural log of P. Here we've got 1 over T. We need the temperature to be in kelvins. If we use Celsius, we could have 1 over 0, undefined. We could also end up with negative numbers, and that messes everything up. So we have to use Kelvin. So we can experimentally determine a heat of vaporization. Here, we've measured the vapor pressure at several different temperatures. We graph natural log of P versus 1 over T. And then we can use something like Excel to give us the slope of the line. So here the slope is negative 3478. And if you do the units, that ends up being Kelvin. Well, that is equal to negative delta H over R. So we can rearrange that and say that delta H is equal to negative slope times R. So there's the slope with the sign changed, multiplied by the gas constant with units of joules per mole Kelvin. And we can say heat of vaporization for this, 28.92 times 10 to the third joules per mole. So there's this practice problem in the book. Vapor pressure of carbon tetrachlorides measured as a function of the temperature, and the results are tabulated. Determine the heat of vaporization of carbon tetrachloride. Well, we have to make a graph and do a linear regression line in order to do this. It's a little hard to demonstrate in a lecture, but we can talk about what you would need to do. The Clausius-Clapeyron equation is natural log of the vapor pressure is equal to negative heat of vaporization over R times 1 over the temperature plus the natural log of beta that we don't care about. So what we need is the natural log of P. So in your spreadsheet, you'd have this data in here, and you'd make another column where you take the natural log of this. So I'm going to stick that over here, natural log And just a quick Excel lesson. Oh, no, I can't remember I don't remember the function for ln. It might just be ln. Okay, skip that. You can do this in Excel, and you only have to type in the equation once, and then you can make it do the rest of the math for you. I'm going to take the natural log of 0.8 on my calculator, and I'm going to write that down, negative 0.2231. When you're doing stuff like this, significant figures get a little wonky, right? It's always better to include too many than not enough. So I'm just going to go overboard a little bit. So I would do that for all of these pressures. Calculate the natural log. And then for the temperatures, I need 1 over the temperature. These temperatures are already in Kelvin, so that's okay. I'm just going to take 1 divided by 200. 0.005. And I would do that for each of the temperatures. Then I graph them with this on the y-axis and this on the x-axis. I tell Excel to give me a linear regression and show the equation, and then I find out what the slope is. Let's just say the slope is 42. Actually, the slope has to be negative. The slope is negative 42. Well, the slope is equal to negative delta H over R. So now it's a matter of algebra. I can multiply both sides by -1. Then I'm going to get that delta H is equal to 42 times R, 8.314 joules per mole Kelvin. And you can calculate delta H. So that's not the answer for this problem, but it's how you would solve it. I won't be giving you a question like this on an exam, right? That's just way too involved. But this sort of process you will be doing in Chem 1B if you take that class. Not on an exam, but in lab. You'll be collecting data like this and doing stuff to it and then graphing it and calculating things like this. It's a very common technique. Any questions? We can also rearrange that equation into a 2-point form. This is something I could do to you on an exam. This is useful for predicting vapor pressure at a specific temperature if we know the heat of vaporization and the boiling point. So we need to know the heat of vaporization. If we know the boiling point, then we have one temperature, and the boiling point is at 1 atmosphere of pressure, so then we also know the pressure. So then if we have another temperature, we can calculate the vapor pressure. This equation and the other one, this is the 2-point form and the regular form. I would give those to you on an exam. I'm not going to make you memorize them. Okay, so here's an example of a problem. Propane has a normal boiling point of -42 degrees Celsius and a heat of vaporization of 19.04 kilojoules per mole. What's the vapor pressure at 25 degrees Celsius? So we're going to use that 2-point form of the Clausius-Clapeyron equation. So the natural log of P2 over P1 is equal to negative heat of vaporization over R times 1 over T2 minus 1 over T1. You'd look that up. So we know what R is. R is the ideal gas constant. Let me write it up here. 8.314 joules per mole Kelvin. It's also equal to 0.08206 liter atmospheres per mole Kelvin, but those aren't the units that we need here. Here we're dealing with joules, and so we want this version of it. So what do we have? We have a couple of temperatures. We have minus 42 degrees Celsius, and we have 25 degrees Celsius. We have the heat of vaporization, so that one's fairly straightforward. We want to know the vapor pressure at 25, but they didn't give us another pressure. When this says normal boiling point, that tells us the pressure. Normal boiling point is the temperature at which it boils at 1 atmosphere. So I am going to call this one temperature 1 and this one temperature 2. Pressure 1 then is equal to 1 atmosphere because of the definition of normal boiling point. So I'm going to put these values into this equation and solve for P2. You could switch the 1s and the 2s. It just gets a little messier with the algebra, and I've done this before, so I'm choosing to do it the easier way. So we've got natural log of P2, that's what we're finding, divided by P1, that's 1 atmosphere, is equal to negative delta H, so that's 19.04 kilojoules per mole, divided by R, 8.314 joules per mole Kelvin. A lot of students don't write the units in. They just stick the numbers in. You really should write the units. There's an issue with the units here. This is in kilojoules and that's in joules. Those aren't going to cancel out. So what I find the easiest to do is to remember that kilo means times 10 to the 3. So I'm going to just erase that. And instead of writing kilo, I'm going to write 10 times 10 to the 3. That's the kilo part. And then what I've got left is joules per mole. Or you can just separately convert it into joules and plug it back in. This isn't proper scientific notation. Your calculator doesn't care. So then I have 1 over T2. Can I put 25 degrees Celsius in there? No, I have to use Kelvin. So this is equal to 298.15 Kelvin. Minus 1 over, if I take negative 42 and add 273.15, I get 231.15. Ah, 231.15 Kelvin. So the joules are going to cancel out, the moles are going to cancel out. It's a little harder to see the Kelvin business. Here I have 1 over Kelvin, so this Kelvin is actually in the numerator. That's going to cancel these Kelvins in the denominator. So I need to stick this into my calculator. I've got a TI-36X Pro, so what I'm going to do is I'm going to do negative 19.04 EE3 divided by 8.314 times, then I'm going to use parentheses, 1 divided by 298.15 minus 1 divided by 231.15. Close the parentheses, press equals. So now I have the natural log of P2 over 1 atmosphere is equal to 2.226 399. Here again, doing significant figures on this is a bit ridiculous. Write down more than you think you need. You'll be safe. Okay, so how do we solve this? We want to know the natural log of what is equal to 2.22. Natural log is a function. You're not multiplying by natural log. It's a function like multiplication or the sign of something. And so we have to undo the natural log. The opposite of the log is called the anti-log. So the anti-log for natural log is e to the x. For base 10 logs, it's 10 to the x. This is e to the x. So I take e to the x of both sides. So that gives me P2 over 1 atmosphere is equal to e to the 2.226399. E to the x. So this is giving me 9.2664. So now I have P2 over 1 atmosphere is equal to 9.2664. If I multiply both sides by 1 atmosphere, I end up with P2 being equal to 9.2264 atmospheres. Now what I would encourage you to do in terms of significant figures is just try to use a reasonable number. And you can do that just by looking at what kinds of numbers did you have here. This is 3, and this is 3, and that one's 4. So you probably aren't going to have more than 4 significant figures. So we'll just maybe round this one to 4 significant figures and call it good. I'm not going to try to trick you on sig figs with something like that. Is that a reasonable answer? The vapor pressure at minus 42 is 1 atmosphere. That's really cold. At 25, which is a much higher temperature, do we expect the vapor pressure to be higher or lower? Higher, right? So we expect it to be much higher. So 9.226 atmospheres. Any questions?